All right, well, good morning, students. So, we're going to be meeting like this for a couple of weeks, and my goal for us this morning is to continue on with some of these basic principles that we're learning for the subject material would be called electromagnetism, but it's the foundation of technology, the way in which circuits work. So 2 weeks ago, you remember we looked at logic gates. Last week, we took a look at how a transistor works in depth with the physics of a superconductor. Today, we're going to go even more basic, but we're going to also advance it to the next level and talk about building a circuit. However, before we can really cover the practical application of building circuits, I need to teach you about three related components of electricity, and those are voltage, amperes, and resistance. So just really briefly, volts are measured in volts, amperes are measured in amps, and they are measuring what's called current, and then resistance is measured in units called ohms. Now, this may be, for some of you, the first time you've heard of these three components of electricity, and so I'm going to do my best to see if I can break it down and make a little more sense for you. Um, I'm also going to have a video linked somewhere here you'll be able to watch where the instructor there helps break it down using the same analogy I'm going to use, but does so in a very clear fashion. So when you think of, and I have a battery right here, when you think of a battery, you need to think that, and they're registered according to volts. This one is a 9-volt battery. Voltage needs to be understood. The technical term is a potential difference between the positive and the negative. So voltage is the difference between those. One analogy you could think of is if you were carrying grocery bags. So if you had a smaller battery like this is only 1.5 volts, and this one's larger, this is 9 volts. You could think of it as the energy that you would take to lift up 1.5 bags of grocery from the ground, and so you're exerting that much energy to hold them because they want to travel down if you drop them, as opposed to this one, which is 9 volts, which would be like carrying 9 bags of groceries and holding all of those up, for they want to be attracted to the ground because of gravity as well. In a similar fashion, you have opposite charges, so positive and negative, always wanting to attract to one another. And when we talk about the flow of electrons inside of here, we're referring not to voltage any longer, but now we're referring to current. There's two different ways in which electricians have understood this. Conventional means where they say that the electricity travels from the positive to the negative. However, that's actually, in physics, opposite. It's the reverse of what's actually happening. What you have is a stored up amount of electrons, and they're all negatively charged. And when you put a negative next to a negative, do they want to attract? No, they want to repel one another. So you have a storage of electrons that want to repel one another, and so in actuality, the electrons are traveling from the negative to the positive, but the conventional form of measurement always goes from positive to negative. Now you can think of that, I don't have a Duracell copper top battery, but you could think of the positive top right here with the nub on the top, and that flows then to the negative. Voltage is the potential difference between that storage and its ability to get to the positive. So here, this would be like only 1.5 bags of grocery that you're having to hold up and could fall. This one would be like 9, so they're a lot harder to hold. You might think of it in terms of a force with the amount of energy you're having to hold those groceries up, that there's more force involved with an increase of voltage. So this is voltage. Current, as I mentioned before, is the actual flow of the electrons. One way that this is sometimes used to teach as a metaphor is that of like a water basin with a pipe that is attached to a tap. So you have a faucet on one end, and if the basin has a large amount of water in it, it will flow out according to how much current is being requested. So current is the flow of the electrons out of how much force that comes from the voltage that could be provided. So the current is largely dependent on the usage. So if I have for example, a computer that's requiring a lot of processor requirements, it's really taxing the processor, it's going to increase the current and thereby quickly, or more quicker, drain the reserve of electrons that you have in your basin of water. So this metaphor of using water is one that the video that is going to be linked is going to display in a little bit clearer imagery. But for now, I want you to think of voltage as being that potential difference for the force that pushes the electrons, and that current is the actual flow of the electrons. Voltage is measured in volts, current is measured in amps. Lastly, and the final component that we need to talk about is resistance. Everything has resistance, but the place where you primarily see resistance will be in the applicational use of electricity. So, for example, a light bulb. A light bulb will have a certain amount of resistance that's going to restrict the flow of electricity. Now, there's a relationship that we use to understand how voltage and current and resistance are all related to one another. And I am going to go through that with you now. Okay, I have got a couple of batteries here, the ones that we were looking at, and here is the relationship between volts, amps, and resistance. First of all, we will measure voltage with the letter V. We will measure amps with the letter I, and we will measure resistance with the letter R, and that's measured in ohms. These three follow a relationship that can be depicted with a pyramid like this. So we're going to make three sections to this pyramid right here, and we're going to put these three in this order. Voltage on top, current here on the left, and resistance on the right. Now, here's why this is helpful. It's because each of these has a dependent relationship on one another. And this little triangle will give you the trick to understanding how to recreate those particular relationships. And here it is. If I want to find out the voltage of a circuit, all I got to do is cover up the V, and this shows me the relationship is current times resistance. So I can write it like this. Voltage is equal to the current times the resistance. If I wanted to find out the current, I would just cover up the option for current, and now I find that it is equal to voltage divided by resistance. So let's draw that one. Current is equal to voltage divided by resistance. And then lastly, if I want to find out the resistance, I can cover up the R, and this will give me what the relationship is here, which is voltage divided by current will tell me the resistance. So this is just a handy, simple little trick to help you remember the relationship between these three, and then a quick way of recreating mathematically how we can determine what those are. Now, there's a few other ways that we can determine what these are on a particular application, and most commonly it's used with a digital multimeter like the one I have here. So I just want to quickly show you how one of these works, and we can take a few measurements, and then we'll get into some more practical applications to talk about voltage, amps, and resistance. as how it relates to technology. So first of all, let's take a look at our 9-volt battery here. This one, I'm going to turn my dial here on my multimeter to where it has battery. Ultimately, you'll see two sides, one with a line and 3 dots under it. That stands for direct current, and one with kind of a wave. It's a sinusoidal wave here that's referencing alternating current, but mine has one specifically for batteries. So I'm going to turn it directly to the 9-volt option, and then I'm going to attach the red to the positive, the black to the negative. I can look on the side of the battery and read positive here is this terminal, and the negative one is here. So we'll put our leads on the negative, positive, and look at the reading. And sure enough, this tells me that it is 9.43 volts. So we know this is a healthy battery, brand new, just out of the bin. A couple of others, I have a AAA battery and a AA battery. Now, you might be thinking that one of these is a higher voltage than the other. In fact, it is not. They are the same voltage, and we can test that as well. I'm going to switch it here to my 1.5 volt option, and then again, hooking up the lead of the positive to the positive and the negative to the negative. You can see the readout here showing that we are actually a little higher than 1.5. So 1.587. And then let's try our AAA, positive to the positive and the negative. Oh, looks like if I can get a good connection, it is even a little bit higher. I keep slipping my finger up. Let's try once more. There we go, 1.6. So this smaller battery actually has just a slightly higher voltage. So you might be thinking, because of the analogy of that water basin idea, that this is a higher voltage than this one. But it's not. Actually, the way in which they're created has the same voltage, the same potential difference between the two. This one is a larger capacity than the other one. And so this one, the AA, will be able to sustain a higher draw of current. So I can pull more amps for a longer amount of time out of this battery than I can out of this battery, but the voltage will be the same. Okay, well, I would love it if you maybe pause this video and go and watch the other one in the link. That's going to help to show you, again, that the metaphor that's used to understand these three components of electricity, voltage being the reservoir of water, current being the applicational use of the flow, and resistance being the tube or the path that allows the water to flow, so that if you have a large opening, like a large sewer drain, you're going to have very low resistance, as opposed to something quite small, like a tiny little tube or an air hose. Something much smaller like a straw is going to have a high resistance. So the relationship between these three components, as you just saw, is one that I'd like us to now try an experiment with of measuring online. So I'm going to have you go to a website that I have linked below, and you can click that and follow along. I'm going to help you with the diagram now. Okay, here is the link to the website, and it is a simulation for circuit building and construction. You can click on this first one for intro. All right, what you'll notice here over on the left are some of the tools that we will be using to build our circuit. Over here on the right is some of the key, as well as some things that you can check on and off. If you remember me telling you how electrons flow versus the conventional flow, we'll leave it on electrons for right now. Values, and then two other ways of looking at it, either as a diagram or the physical representation that we have over here. So you can leave essentially everything just like you find it once you click the link. And so let's begin now with building a simple circuit and then taking some measurements. So we're going to start with our battery. Just click and drag. You'll notice a couple of properties here about the battery. The little dotted red lines are where we will connect other components on both ends. You have the positive here, negative here, and if you were to click on the battery itself, it will bring up a little place where you can change the voltage. We're going to change ours to 12. So this is going to be a little 12-volt battery. You can just click anywhere to get yourself out of that. All right, next thing we're going to do is grab the switch, click and drag that, and as we do, you see the switch can be turned on or off. So this is open and this is closed. we are going to leave it open for the time being. You just grab this component and then hover the red ones over one another. You'll see that they will link up just like that. If you ever want to unlink two of these, you can just click right on the selection that you've made and then click the little scissor icon here to then separate them once more. So we're going to keep them linked for now. All right, let's attach a wire then to this side and bring in another wire and another wire. Let's attach these here so that we start to build our circuit. And we'll do the same over on this side. Few more pieces. Good. All right, at this point, we will bring in our light bulb. Now, a light bulb has resistance built into it. And we have another component here, which is a resistor. This is what a resistor looks like. This one is set at 10 ohms, and we are going to turn that down to 3 for right now, and we'll leave that one there. And we're going to do the same for our light bulb. We'll turn our resistance down to 3 ohms. All right, for our light bulb now, you can connect it up to the circuit, and you won't yet see anything happening here because our switch is still open, but as soon as we close it, you will notice the light bulb shines brightly, and here we see the flow of electricity with the electrons moving from the negative side to the positive side. If you wanted to switch this to conventional, you can click that over here, and this is how it normally mathematically is used to understand circuits, but we'll have us showing the physical representation for now. All right, let's open it back up. And now I'm going to have us bring out our voltmeter. Just like the multimeter that I was showing earlier, we will take the negative end and attach it to this side. In fact, if we just set it right here anywhere over the wire and the positive on the positive, you'll notice it will read our 12 volts. But if I move it over past the switch, well, now it's off. When we're taking our measurements, it's always best, especially when we start adding other components, it's always best to measure right across wherever the load is. So we're going to move both of these up on either side of our light bulb, and now when we close the circuit, we see that it reads 12 volts. Now if you can remember, the particular equation that we used with the picture of the pyramid for voltage was current times the resistance. And if we are going to determine that, we actually have already the resistance here at 3 through the light bulb. And I'll just click on this again so you can see resistance is 3. The voltage is 12. So what do you suppose the amperage is going to be? Well, remember, amps are measured by volts divided by the resistance. Voltage was 12. Let's just turn this on again so we can see, right? Voltage was 12. Our resistance was 3. So if you're doing some quick math here, you might determine, and I'm just going to grab our little crosshair here to put this over on this side. Right now it's not reading any amps because our circuit is open, but as soon as we close it, remember the equation, voltage divided by the resistance. So this would be 12 divided by 3. What is your prediction? Are you ready? Well, let's see. Let's close it. And sure enough, we end up having 4 amps. So this lesson has primarily been about trying to help us to understand within a direct current circuit the relationship between voltage, amperage, and resistance. And as you have some time, I would encourage you to play around with this program a little bit. You can take your ammeter and just set it back over here to return them to the dock. You can also click this little button right down here in the corner, and that will reset the screen so that you can build anything new. One of the other components that I'd love to cover with the class is that of conductivity. So if we take our light bulb here and delete it, and if we can replace it with a resistor, you will see, bring out back our ammeter again. You remember our voltage out of the battery is 12, our resistance here is 3, and so even in this same circuit I should end up with an amperage of 4. But what would happen if we open our circuit and then delete here our resistor? And there are some other items that we could put inside of this circuit. If you click the down arrow, you will see there's a fuse. And if we insert our fuse and then hook this up to our circuit, clicking on our fuse, we'll see it's rated right now at 4 amps. So when I close the circuit, oh, sure enough, the fuse breaks. So if we click the fuse again and give it a higher rating, now for 5 amps, now we should be able to, well, and I'm going to have to reset this. There we go. It's still breaking, and part of this is because we have no other resistance in our circuit. So for that to be fixed, let's put this back to 4, and now we're going to take that resistor that we used earlier. Let's make sure that it is set at 3, and let's bring this in. Now when we repair our fuse, sure enough, we find because we have limited our current down, that even passing through here, it stays just under 4 and our fuse doesn't break. There's a few other items that you are welcome to play with for connectivity. I would encourage you to play around with a few of them. I'll just briefly show them to you here. What would happen if we put a paper clip in? What would happen if we put a coin in or a dollar bill? How about an eraser or a pencil or your hand or a dog? And so you can play around with this a little bit. What would happen if we hooked a dog up to our circuit? And I am going to save this for you to try on your own. Okay, students, thank you. That is our lesson for today. Spend some time, if you can, review the video that's linked here in the description. And then also make sure you click the link to go and work on the project page there from University of Colorado at Boulder. So that program is a lot of fun. Familiarize yourself with it. We will be revisiting it next week, continuing to study circuits. Okay, well, I hope you guys have a great week. Stay safe and have fun.